Thank you all for being here. Thank you for taking the next 8 minutes to listen to me. And I feel like I could not be any more different than the previous speaker. Starter and I will have data for you. I'll have data slides and probably way too many slides to get a message across. But let's start with introductions. So my name is Jana Kainerstorfer. I am an associate professor in biomedical engineering. And the talk title is, when I put together those slides, I realized I am by no means in a position to tell you about best practices. So really the change of the talk is my experience so far. I'm pretty much going back to Jeff's point, why faculty members are terrible entrepreneurs and what are the hurdles that we need to overcome in order to actually bring something to the market, let's say. So I thought I'd start with where I'm from. Well, I'm born and raised in Vienna. I got officially all my degrees are from Vienna. But I've been in the US for 16 years now because I was an undergrad and I was an exchange student at Georgetown. I ended up spending an additional year there doing all the research for the master's, and then went to a conference at NIH and just talked up this guy, and who ended up giving me a job as a PhD student, was an advisor at the medical school in Vienna. So I'm a physicist with medical influence doing all the research at NIH. And then I met someone else just by coincidence, got my postdoc training at Tufts, like so many other biomedical engineers, went the Boston route. And then I got a tenure track position at Carnegie Mellon University. And for anyone who's not an engineer in this room, CMU is top 3 or 4, depends on the year, engineering schools in the country, top 10 in the world. So I've been there for 6 years now, got promoted to associate professor, but that does not mean tenure yet. So I thought I do want to tell you about some of the research we do, because I think it's a good example of potential research that can be taken to market, but also point out of why during the tenure track, it's almost an impossibility. So I will start with data. And I thought I'd tell you what we do in the lab, and it's very simple. We develop very fancy pulse oximeters. Anyone who's ever been into a hospital knows shining light through your finger tells you how oxygenated is your blood, especially during COVID. That's a very important marker. It really is based on the fact that red light gets absorbed by tissue. Everyone knows what I'm talking about in the sense of if you put a flashlight in your mouth, your entire head lights up red. And depending on how much red light comes out, that tells you about oxygenation in the tissue. So we built this, we use this, we do that for brain imaging. We put LEDs, laser pointers onto the head and measure whatever light goes into the brain. And then we can say something about brain function and showing you squiggly lines here that essentially represent functional activation in the brain. So 2 applications that we have in the lab that I believe have commercial value, that's my opinion, is we're looking at traumatic brain injury. So that's one project that I'm talking about. And the other one is for fetal health monitoring. So let's start with traumatic brain injury. If you are in a car crash, pretty much clinicians want to know, is your brain okay? In particular, one of the things that are being asked is the pressure inside your brain okay? Is the brain swelling? Is there bleeding? And so on. So what are the ways of how we can measure pressure inside the head? Well, the clinical standard is drill a hole, put a pressure into the brain, a pressure probe inside the brain, and measure it that way. Obviously, that's not often done because that's highly invasive. So what we have done is we've taken our optical approaches, we've developed, we're measuring stuff in the brain. We're measuring blood flow changes. It's essentially a fancy pulse oximeter for the brain. And we're using the signals with a little bit of machine learning to convert it into intracranial pressure. And here are my data slides. The x-axis is the ground truth. The y-axis is our algorithm. If everything works, all the data points should be on the 45-degree line. And we see many, many different data points that highly correlate with each other. And so essentially what this data slide is saying, or rather this one, within 4 millimeter mercury accuracy, we can quantify pressure inside the head. Now, what does that mean? 10 millimeter mercury is clinically relevant. So we're much better than that. This data is from animals. We are now translating it to children in the pediatric ICU. And I'm showing you the same kind of squiggly lines or dots, essentially saying we can do it in humans. This is outstanding. There are so many different applications where this is important. And I'll talk about commercial implications in a second. The second project I want to tell you about is fetal health monitoring. Right now, any woman that is pregnant, you can use ultrasound for structural changes. You can look at the heartbeat, but it doesn't really tell you anything about fetal hypoxia. About 300 C-sections in the US per year are performed in terms of as an emergency surgery because of suspected fetal distress. There is a huge inaccuracy in determining when fetal distress is really happening. And so there's a gigantic need to reduce C-sections by more accurately determining, is the fetus, especially during labor, is the fetus in distress? And so what we're developing is essentially a fancy pulse oximeter for the fetus by putting some optical probes on the abdomen of the mother. And we have some preclinical data, and I will not, those are really not easy understandable yet, but essentially we're at a point where we're saying, okay, we can measure the fetus, which is from an engineering perspective already outstanding, optics perspective outstanding. We measure the fetus, we measure the fetal heart rate optically. We can translate that into changes in oxygenation over time. So this was all done in animals. And we're translating it to humans right now. Okay, I can give talks about my research. I can sell the ideas to get research funding. I can publish papers on it. And throughout my last 16 years, I've published quite a few papers. And I looked back, and I'm only going to focus on my own publications here, but I realized that pretty much from my PhD work on, where I published a paper with 7 patients. And then during my postdoc, maybe with 5 or maybe, 29 patients. That was a large study. Just recently 13. And the really big one right now is based on 5 animals, not even 5 humans. So the point I want to make is that we publish papers in biomedical sciences very often, especially when it comes to clinical translation of methods that we're developing with very small sample sizes. I've told you 300,000 C-sections per year are performed potentially unnecessarily because of suspected fetal distress. I'm probably going to publish a paper with about 20 women and call that proof of principle. And it's good enough for academia. And so the reason is because of what tenure and promotion really looks like. And so I put together this slide actually recently for some of my students because they asked me, well, what does it actually mean to be on the tenure track? Again, I'm not tenured yet. And essentially the criteria are do good work. If you do good work overall, that's kind of the statement that my dean would tell me, do good research, you'll get tenure. And tenure is supposedly this somehow magical time point where then afterwards you have no longer any pressure, which is also not true. But in any case, you get a lot of resources to achieve something. So what is that something? Do good work, get funding, graduate students. The more PhD students I graduate, the better I am. I should mentor my students. Hopefully I teach well. Be visible, give research talks, publish or perish is the tenure track, as we often say. And we also have to do a lot of service inside and outside the university. And so ultimately, this is actually copied from our internal handbook of what promotion and tenure should look like. Ultimately, what it boils down to is you're supposed to be on an upward trajectory of like develop new things, publish more papers, graduate more students, and so on. And it's all well and good, except for that it really does not support entrepreneurial work. none of the requirements for me getting tenure actually include impact in the sense of, especially in my field. It does not include any criteria about how successful will I be diagnosing a disease? How successful can I treat a disease? Or how many patient lives will I be saving? This is not a criteria in the tenure and promotion package. And so the problem also then, even if I want to focus on this and say, all right, well, I personally really want to see my research in the clinic and support it, and I don't want to just have a patent, sell it off to a company. I actually want to be involved in the development. Well, I also need to consider funding opportunities for some of the research. And how do I go from 5 patients to 5,000 patients? Well, for me, as in academia, one of the avenues, especially in biomedical engineering, one of the ways I get funding, and one of the ways that I'm almost required to get funding, is federal funding, especially for us, that's the National Institutes of Health. And there's the big award, it's called an R1 award. It's a 5-year funding, multi-million-dollar grant. Essentially, I'm going to get judged based on significance, innovation, and approach. And the argument I'm going to make is, or sorry, the aspect on innovation is taken from the NIH website. The reviewers are asking if my grants, if my ideas are innovative in the sense of, does the application challenge and seek to shift current research or clinical practice paradigms by utilizing novel theoretical concepts or approaches? So if I want to go from 5 patients, 10 patients, and I already published a paper, and I'm writing a grant of saying, all right, now let me figure out, does that work, does that instrument that I already built, does it work in 1,000 patients? I'm not going to get funding from the NIH for it, because the NIH is not going to fund that, because inherently it's not going to be innovative, because I already have shown, I've already published a paper on it. So that's one of the hurdles. But also, if I tell my students, well, change the instrument, make it better, make it sampling frequency better, resolution better, better imaging and whatever, then it might be innovative, but that's actually not a good idea if I ever want to consider FDA translation. Because FDA regulations for the medical devices that I would have to get in order to show its efficacy and such really does not support me changing the instrument. You want to have the same instrument over a large sample size and show efficacy. So my argument is that, well, this is taken from, sorry, it's kind of a blurry image, but this is taken from the FDA website that essentially shows the life cycle of medical devices, in this case, what I'm talking about. We're starting with discovery, intervention, preclinical, clinical, and then eventually get into regulatory and product launch timeframes. And my argument is that while on the tenure track, while I have to prove myself that I can get more papers, more students and such new work, really an FDA regulatory path all the way to product launch is not something that a tenure track really supports. And so none of this life cycle aligns well with the tenure track requirements. So the solutions that I've taken for those 2 projects that I was telling you about is, I really wish I had a logo on the left-hand side. I thought I would by the time I'm giving this talk. I'm in negotiation right now with a large company that I'm not allowed to disclose yet, but essentially a company I have managed to get interest from a large pharma company, I guess that's what I can say. They really want me, they want to give me money to show in a large clinical trial, as in hundreds of patients, if our non-invasive pressure sensor really works. And I'm okay taking this on because I'm close to submitting my tenure package. I would not be able to say yes to this if I were still starting out. But also it's all going to be based on me hiring technicians rather than PhD students. As I said, I mean, I want to show efficacy in hundreds of patients. That's not a PhD thesis because there's no innovation in there. The other side, the fetal pulse oximeter, I'm collaborating with a company. It's called Radiant Oximetry. And so we've been working together for a few years. And so they are really taking care of all the actual building of the hardware and clinical translation and taking data. And we have SBIR funding, which has been mentioned multiple times earlier in this discussions as well already. So it's a really nice way during the tenure track to work with a company, have them see it through and still have a PhD student just develop the novel algorithms, which may not go into the company itself, but that's okay. So those are my solutions for now. By no means the only ones out there. Just again, this is my own personal story here. The problem with SBIR funding, even though it sounds magical, it's like, okay, you have a company that does all the marketing for you and are entrepreneurs that I am not. The problem with SBIR funding is that typically they only fund phase 1 NSF or NIH. It's only 6 months long. Phase 2, which already is supposed to be really amazing funding, which we do have, is only 2 years long. And 2 years in the life cycle of a PhD student is nothing. As soon as I take on a PhD student, I'm required to find funding, not like in Austria where PhD students might be covered for all the duration, the time they're there. I am required to find for us about $80,000 a year for a PhD student, and I'm guaranteeing them funding for 5 years. So after the SBIR is done and they want to write one coherent PhD thesis, that's really not enough funding. So there's this caveat with SBIR funding. So my conclusions are really meant to just essentially point out the difficulties tenure track faculty members face, maybe some ideas as well. So really what I'm saying is that the early career tenure track faculty really do not have easy resources to do clinical translation or actual large-scale translation in whatever field they're in, and seeing something through, because the requirements of the tenure track do not support entrepreneurship. There are options of SBIR funding and industry-sponsored research. As I said, they have their own caveats. And so I thought I'd just point out some of the opportunities I'm seeing, and I think that goes hand in hand a little bit with what our previous speaker just said, is, well, how about we change student requirements? How about we actually create, and that's more specific for the US, I guess, but how about we change PhD requirements to not be based on, you get a PhD based on how many papers you have published and how many conferences you attended, but maybe about, have you thought about starting a company and taking your PhD research further? And then also, I think some of the NetSmarter University, higher level university in the US ideas of changing tenure track requirements, I would really encourage tenure track requirements to be different nowadays and encourage collaborations with industry, and as much as encouraging faculty members to get federal funding, and really also maybe change the shift of, and that's been said earlier before, I don't remember how it was phrased, but maybe we should not consider success a question of what is the H impact, but what impact does my research really have? And so in my case, do I have a clinical impact? And I said, I started out my tenure track position during my 7 years ago, when I interviewed at multiple different universities. There's this typical question of, what do you want to be known for? And I never answered about developing something new. I said, if I can save one single patient's life, that will be impactful. And so maybe we should consider impact differently than an H index. So with that, I just want to say that I have a ton of people in my lab. It's just customary for us in engineering to thank all the people. So thank you for your time and listening to me.